Lesson 2 is our second of 3 lessons on number, and just thinking about how this course is set up, our first 25 lessons, or the first quarter of the course, is basically a review plus introduction to the 10 major topics that we're going to cover. So you'll get introduced to those 10 major topics, the first one being number, and then throughout the course we'll learn more and more about each of those topics, and the main focus here is Algebra 1. So you should have read over your rules and definitions for this lesson. Let's go ahead and look at Part A, the origin of modern numerals and arithmetic symbols. And so we talked about the history of mathematics some in Lesson 1. We talked about the Hindu-Arabic numeral system and Hindu-Arabic digits. Those include 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are what pretty much everybody in the world uses now when they're doing mathematics. Now, you might also see Roman numerals used as well. They're not real common, but sometimes you might see them on a clock. That's one common example. And these symbols, they have meanings to them, just like the Hindu-Arabic numerals have meanings. So if we look here, the capital I, that stands for 1. X stands for 10. C for 100. M for 1000. And V, that stands for 5, L for 50, and D for 500. Now, using the Hindu-Arabic system, if we saw this, we would just say, well, that's 162. We wouldn't think of that any other way. But in Roman numerals, those are added together. For example, if you saw this, C, L, X, I, that would tell you to add 100, because that stands for C, right? 50, because that stands for L. 10, because that's the X, and then 2. And so we'd say 100 plus 50 is 150, then add 10 to that, that's 160, add 2 to that, that's 162. So CLXII, that equals 162. Now, if you see a smaller Roman numeral preceding a larger one, then you subtract them. So, for example, if you see an I, then a V, that's a smaller numeral, 1, preceding the 5, that means do 5 minus 1 equals 4. So IV equals 4. And so hopefully you could understand IX, that would be 9, because it'd be 1 taken away from 10. XC, that would equal 90. 10 taken away from 100. IC, that would equal 99. 1 taken away from 100. Now, what if you had DXC? It's like a bigger number, smaller, bigger. Well, you'd say, well, D is 500, then XC is 90, so DXC, that equals 590. Now let's look at some different number systems, not just numerals, but number systems. And like we have the Hindu-Arabic numerals that pretty much everybody uses. Pretty much everybody uses the base 10 number system, where you have your ones place, your tens place, hundreds, and so on. So why do we call it the base 10? Well, the ones place right here, that's equal to 10 to the power of 0. So a base 10, an exponent of 0. Anything to the power of 0 equals 1, actually. But then we have 10 to the first power, that equals 10. 10 to the second power, that's your hundreds place. 10 to the second power, that means 10 times 10. 10 to the third power, that means 10 times 10 times another 10, a third 10, and that equals 1,000. That's your thousands place. Now 10 to the minus 1, that's 1 over 10. That's your tenths place. 10 to the minus 2, that's 1 over 100. That's the hundredths place. 10 to the minus 3, that'd be the thousands place. So we have a base of 10 there. Now, a system that you're probably not as familiar with is the base 2 system, and that's actually really important with computers. We'll study it more in lesson 25 with computer math. 2 to the 0, that's 1, that's your ones place. 2 to the 1 is your 2's. 2 squared is your 4's. 2 cubed is your 8's. There's only 2 digits in the base 2 system, 0 and 1. There's 10 digits in the base 10 system, 0 through 9. Here it's just 0 and 1. And think about computers. Computers have to do a lot with electric current. Electric current's either on or off. So on is 1 in a computer, off is 0. So let's do an example here. And this is our first example problem, and so you always want to make sure and do all of the example problems. You don't have to write it out, you just need to solve it. So let's convert the binary number 1011 to base 10. And so how do we do that? Well, first let's just write it in here. 1 1 0 1. Okay, and so think about these as on or off. If the 2 to the 3rd spot is on, there's a 1 there, so that would be an 8. Then 2 squared, that is off, so that's a 0. Then 2 to the 1 has a 1, it's on, so that'll be a 2. And then 2 to the 0 is on, so we need to put a 1 there. And then we just add those together. 8 plus 2 is 10, plus 1 is 11. And so that would be the base 10 conversion for 1011. So the base 2 system, that's important in computers, computer programming. And if you look on a computer, a lot of times there will be a place where you can find the display, the computer display, and its color quality. And like here it says 16-bit, medium, and then highest color quality is 32-bit. Well, what that means is there's 2 to the 16th possible color combinations. And that's a pretty big number of color combinations. And then you also have a 2 to the 32nd, a 32-bit. So 2 to the 32nd possible colors. So it is good to know how that binary system works. Now let's look at some arithmetic symbols, and just think about, why do we do a plus sign, a minus sign for subtraction, an X looking symbol for times, or we also use a dot, or sometimes we use parentheses for multiplication. And then division has this line with a dot above and below it. Where did those come from? Most of those symbols were first used in arithmetic and algebra in the 15th through 17th centuries. So compared to the history of man, that they're not that old. It's important to remember too, we use the plus and the minus to represent positive and negative numbers too, like a +3 and a -3. So mathematics, it's considered a symbolic language, and a lot of times it's just for efficiency. Think about in the 15th through 17th centuries, they didn't have computers, people had to write everything down, and instead of having to write the word plus, you just do 2 little lines like that. That takes up a lot less space, and that can make mathematics confusing though, because one little symbol can mean a lot. So mathematics has a symbolic language. The symbols may represent a word, they may represent a sentence. It's basically its own language. And like we said in lesson 1, it's the language of science. And because it's the language of science, therefore it's a tool for studying God's creation. Let's move on to part B on types of numbers and number lines. And for this first part on types of numbers, you can refer to the lesson 2 definitions for the different types of numbers. And so you'll have problems in your problem set that will help you think about and compare and contrast the different types of numbers. So look at example 2.2, true or false. All real numbers are also integers. Well, integers don't have decimals, right? Those are non-decimal numbers. Real numbers, they can be like 3.14, 1.77. So this is false. It would be true if it said all integers are also real numbers. That would be true. And you can pause the lecture and go ahead and try to answer these questions before I do, and then you can turn the lecture back on and see if you did them correctly. You don't have to wait for me to explain it. You can pause it and try to answer it on your own. So example 2.3, true or false, all counting numbers are whole numbers. Well, whole numbers start with 0, right? 0, 1, 2, 3, 4. Counting numbers are like counting on your fingers. You start with 1. So counting numbers would be whole numbers. All of them would be. So this would be true. Now let's look at a particular two types of numbers here, real numbers and irrational numbers. Real numbers, those include all positive and negative numbers with and without decimal places. So we also have rational and irrational numbers. And rational numbers, those are numbers that you can write as a ratio of integers. So 10 over 2, 7 over 5. Rational numbers, again, those are a type of real number. They have a decimal form. All fractions have a decimal form, right? 10 over 2. We could write that as an integer, 5, or as a decimal, we could just say 5.0. 7 over 5, that would be 1.4. Now, what if we had 1 over 3? Well, that would actually be a repeating pattern. It's 0 point, and then that 3 would just repeat on and on and on, and it would just repeat on. And so one way that we use to describe that repeating pattern is we would just say 0.3 and put a bar over the 3 to say that that 3 is repeating. Now, numbers that don't have a repeating pattern to their ratio or can't be written as a ratio of integers, we call those irrational numbers. They have no recognizable repeating pattern, no matter how many decimal places you try to show. So pi, for example, 3.141592653, and so on. It doesn't have a repeating pattern to it. Neither does the square root of 2. In fact, there's a lot of numbers that are irrational. Remember, we talked about in lesson 1 how the square root of 2 caused the Pythagorean number worshiping cult to disintegrate because they couldn't write it as a ratio of integers. They couldn't find a ratio of integers that worked for it. But as far as we know, it has an infinite non-repeating pattern of decimals, which is pretty interesting. Now, you might be thinking, if there are real numbers, are there imaginary numbers too? I mean, why would we have to classify things as real numbers? Well, actually, there are imaginary numbers. We also call them complex numbers. We'll talk about them later. Let's go ahead and talk about some ways to organize numbers first, though, and look at number lines. Number lines, those are a useful tool for understanding signed numbers, meaning like plus and minus signs, positive, negative signs. So here's a number line. And you can see there's just like a horizontal line there with evenly spaced marks on it. It's got arrowheads on the end of it. It kind of looks like a ruler, right? That's what a number line is. And has a 0 point there, negative to the left, positive to the right. Why don't we go ahead and do an example? Organize the following numbers by graphing them on a number line. Well, so what we can do is, let's see, we have 4.1. Let's do that first. So we can put a dot about where we think 4.1 would be. So right about there. And I'll just put a line up to that saying that's 4.1. And then 2, well, just put a dot on the number line where 2 is, and we'll write 2 right above that. 6 and 3/4, well, that's between 6 and 7. So we could say maybe about right there. We estimate when we put it on the number line. It's not as exact as writing it out. We have to estimate a little bit where the 3/4 mark would be between 6 and 7. And then -2, well, that would be here to the left. And so one thing this helps us see is just the size of the numbers relative to each other. So -2 is to the left of 0. It's 2 away from 0, just like +2 is. +2 also has a distance of 2 from 0. It's just in the opposite direction. Now, another type of number is squares and square roots, and we looked at those a little bit in lesson 1 when we were talking about the Pythagoreans and the Greeks too. The Greeks' religious worship of human reason, that caused them to ignore some aspects of reality that defy human intellect, that we don't totally understand. So they would just ignore them. For Christians, though, concepts that confuse the Greeks, like infinity and irrational numbers, those aren't a problem for us because God is eternal, so that helps us understand that there would be infinitely large numbers. God is omniscient or all-knowing, not us, so numbers that we can't make sense of, that we can't find the last decimal place on, those are okay with us. So like the square root of 2, an irrational number, there's no simple way to write that. It has a non-repeating decimal pattern. But the Greeks found that you could make a square, and it has square corners or right triangles, and the square has a diagonal, and you can kind of see the triangle that forms there has sides of equal to 1 each, and then the diagonal is equal to the square root of 2. So they could draw that. They could use geometry and draw the square root of 2, but they couldn't use numbers to come up with a ratio of numbers that was equal to that. And that's one reason they shied away from algebra and arithmetic, because it didn't make sense to them. They called it irrational, hence irrational numbers. So when we have squares and square roots, there's some comparisons there, and so I have this table over here, and n and n squared, where n represents any number, so that could be a 1, a 2, a 3, a 4, whatever it is. So you square that, square a 1, 1 times 1 is 1, 2 times 2 is 4. Now go the other direction though. If you have a 4, the square root of 4 is 2. And same with any of those. You go right to left, you would say, well, the square root of 16 is 4. The square root of 25 is 5. And remember, math is a symbolic language. That symbol right there means the square root of. So you say the square root of 25 equals 5. So this is a good table to memorize. Memorize all of these squares down to 13 times 13 is 169. Once you pause the lecture, see if you can do example 2.5. Find the value of each of those. Square root of 36, square root of 9, and square root of 121. Well, hopefully you just look at that chart. Square root of 36 is 6. Maybe you have these memorized. That'd be great. You should try to memorize these. It'll make your math go faster for you. Square root of 121 is 11. Well, now let's talk about complex numbers. And remember, we said we were going to talk about imaginary numbers, numbers that aren't real. Well, we also call those complex numbers. And let's think about square root a little bit more. Like we had the example square root of 25, and when we're trying to find the square root of 25, we say, well, what two numbers multiplied together that are both the same, what two numbers could we use that equal 25? Well, that would be a 5, because 5 times 5 equals 25, right? So the square root of 25 is 5. Well, what about the square root of -1? Well, what two numbers can we multiply together that are the same number that would equal -1? Well, 1 times -1, that equals -1. But those are different numbers. That doesn't work. -1 times -1, that'd be a +1. That doesn't work either. So there aren't two numbers that we could multiply together. That's what we call complex numbers. So if we have a square root of -25, what we do is we turn that into two factors, the square root of -1 times the square root of 25. And the square root of -1, we just refer to that as I, because it's easier to write an I than the whole square root of -1 thing. So we just say square root of 25 I. We put that I on the outside of the square root symbol. So look at this here. I, that's equal to the square root of -1. I squared equals -1, because that would just be square root of -1 times the square root of -1. That equals just -1 without the square root symbol. same with any number. Square root of 5 times itself, square root of 5, that would equal 5. So let's do some example problems. Simplify these. What would the square root of negative 19 be? Well, you should think, oh, that's a complex number. And the proper format for them, it's not that it's wrong to leave it square root of negative 19, it's just the proper format is to get rid of the negative sign. And so we would say square root negative 1 times the square root of 19 is equal to the square root of 19 times I. So it's just easier to write I than it is square root of negative 1. Again, that's why we use that. Square root of negative 16, let's look at that. Again, we would just say square root of negative 1 times the square root of 16. Now the square root of 16 is a 4, right? So this just simplifies to 4i. And then let's do one more, 5i squared. Do that right here. Well, 5i squared, remember I squared is negative 1, so I'll just put that in parentheses there, negative 1. 5 times negative 1, well, that's just going to be negative 5. Okay, so that's an appropriate way to write that, negative 5. So when you see a problem like this and it says to simplify it, that means one of two things here. Get rid of that I squared term, make that a negative 1, or get rid of the negative inside the square root symbol by factoring that out. And remember too, when we write something like this, square root of negative 1, we're multiplying by square root of negative 19. That's what we say when we're factoring out that square root of negative 1. Let's move on now to arithmetic review in part C. And we discussed place value in 2A, and in basic arithmetic it does help to consider place value in our 4 operations: multiplication, division, addition, and subtraction. It's also good to think about fact families. So we have addition, subtraction, fact families, multiplication, division, fact families, and how addition undoes subtraction, multiplication undoes division, vice versa. So we'll think about some of those things as we do this. So here, let's use the example of 153. Think about Jesus after the resurrection. He led the disciples to a place where they caught exactly 153 fish. So an interesting number to use here. 153, it's composed of 100, 5 tens, 3 ones. Using addition, we can write it like 100, 5 tens is 50, 3 ones, that equals 153. Now each of those numbers added together is called an addend, and the result is called the sum. So let's do an example here. Find the sum of these. And so again, you can pause the lecture if you want to and solve these on your own. Or if you're really rusty with your addition, then you can follow along here. So let's add these first in A. 7 plus 1 is 8, plus 6 is 14, so we write a 4 here. Bring a 1 up to the tens place, because it's in 14, right? So that would be, the 1 would go in the tens place. And so then we add 5 plus 5 is 10. Then we have 2 ones there, right? The yellow one that I wrote on top, and then the one underneath. So that would be 12 total. So we put a 2 here and a 1 here in the hundreds place now. And we add the 3 and the 1, which is 4. So 424 is the answer there. B, minus 4 plus 7. We might like to use a number line there, and we could start at 0 and move -4, move over to -4, and then 7 to the right, positive 7. So we go back 4, 5, 6, 7 right there. So if we want to use the number line to add a negative and a positive number, we start at 0. We always start at 0 on something like that. Move the negative amount to the left 4 and then add 7 to that. The order doesn't matter though. We could have added 7, then moved back 4. We still would have ended up at 3. So that would be the answer there. We don't have to put a plus sign in front of it either. We can just write the number 3 and it's understood that's positive. Now the last one there, $27.95 and $14.15. Let's line them up relative to their place value. So we use the decimal place to help us with that. And so we'll put 1.5 here and then 1.4 here. And so we have them lined up with the appropriate place value. That's very important. So we'll just add 5 and 5 is 0, carry 1. 9 and 1 is 10, plus another 1 is 11, so a 1. Bring down the decimal place also, carry a 1. 7 and 4 is 11, plus 1 is 12, so put a 2 down and bring a 1 up to that tens place. 2 plus 1 is 4. And so that's 42.10, and we'll put a dollar sign there out front to remind us it's money, $42.10. Let's do some subtraction now, and in subtraction you always need to have a larger value on top of a smaller one. That's a good thing to remember. So example 2.8, let's check the result of example 2.7c by subtracting 1450 from 4210. Does that equal 27.95? Remember, subtraction should undo addition. Well, let's see, 4210 minus 1415. So we want to put the larger number on top of the smaller one. And so let's subtract. So we have a 0 minus 5 there in the hundredths place to subtract. Well, we can't do that. We can't have a smaller minus a larger. So we have to borrow from that 10 right there. So we borrow 1 and we bring that over and we make this a 0 up above it. 10 minus 5 is 5. Now we have a 0 minus 1. Well, we can't do that either, so we have to borrow from this 2, make that a 1, and bring that over. So now we have 10 minus 1 is 9. Put our decimal place down. Now we have 1 minus 4. Again, we can't subtract like that, so we have to borrow. So 3, borrow from that 4, bring a 1 over, and we have 11 there. 11 minus 4 is 7, and then 3 minus 1 is 2. 27.95. That's what we expected, right? We expected to get that. So we can check the result of addition by doing subtraction. Look at example 2.9. Find the difference between 108 and 255. So when we see a word like that, difference, that tells us to do subtraction. And so we would do 255 minus 108. So that goes on the bottom. Put a subtraction symbol there. 5 minus 8, we can't do smaller minus larger, so we have to borrow. So we'll make that 5 a 4 and bring a 1 over. 15 minus 8 is 7. 4 minus 0 is 4. 2 minus 1 is 1. So let's check by adding 147 and 108. Now here it doesn't matter if the bigger one is on top or not, right, when we're doing addition. Let's add them up. 7 plus 8 is 15. Carry 1. 4 plus 1 is 5. 1 plus 1 is 2. We got back to 255. So that helps us know that we did the subtraction correctly, and that answer 147 is correct. Let's move on to multiplication, and remember, this is a review here. You should be pretty familiar with arithmetic already. This is for people who really need to brush up on their arithmetic. If you're already really good at arithmetic, you can just go ahead and go on to the problem set. But if you need help, just be patient here. Now let's think about multiplication a bit. Multiplication is basically a fast way to add. When you have equal groups of things, so 4 groups of 7, that would be 4 times 7. 2 groups of 5, 2 times 5. The result of multiplication, that's called the product. The numbers that are multiplied together, those are called factors. So let's do some practice here. Find the product of 24 and 315. So when we multiply, we want to put the bigger number on top. So we'll put 315 here, 24 here. And we need to think about place holding as well as we do this. So we'd say 5 times 4, we'll multiply everything on top by the 4 first. 5 times 4 is 20, so a 0 here, carry a 2. 4 times 1 is 4, plus 2 is 6. 4 times 3 is 12. Okay, next we do the 2. Multiply it by everything on top. Now, we need to hold the place of the 2 is in the tens place, right? So we don't put anything there. We could put a 0 just to hold the place. And then we'll say 2 times 5 is 10. So we need a 0 here, carry a 1. 2 times 1 is 2, plus 1 is 3. 2 times 3 is 6. And then we just add both of those rows together now. 0, 6, 5, 7. 7560, that's the product. So we'll just write that over here. 7560 is the product of 24 and 315. And then example 11 there, find the product of 1.3 and 22.4. So here we have some decimal numbers. Well, what we want to do here is just multiply the numbers. Forget about the decimals right now. Count them up though. We have 1 decimal place there and 1 decimal place there. One digit past or to the right of the decimal place in each. So our decimal total is 2. So let's just write that number over here. And now let's just go do 224 times 1, 3. 224 times 13. We're not worried about the decimal places right now where those occur. So we'll do our multiplication like we did before with these two factors. 4 times 3 is 12. Carry 1. 2 times 3 is 6, plus 1 is 7. 3 times 2 is 6. Now let's multiply everything by the 1. That's in the tens place, so we need to hold the ones place there. And so 224 times 1 is just 224, right? So we'll just say 2, 2, 4. Now let's add them together. 2, 7 and 4 is 11. Carry a 1 there. 6 and 2 is 8, plus 1 is 9, and a 2. 2, 9, 12. Now, we need to put that decimal place back in, and there's 2 places. So we always start on the right here, to the right of the number. That's where the decimal point goes, right? If it's not there, it's understood that it's there. And we'd move to the left 1, 2. So the answer is 29.12. 29.12. So what did we do there different than problem 10? Well, we counted our places to the right of the decimal point, added those up for both problems. We had 2 total, and then we went and just did our multiplication without any decimal points in it, got the answer, then put the decimal place back in. Okay, last let's do division, and this is usually the most challenging operation for students to do, and that's why we're saving it for last. And multiplication, it can be undone by division, just like addition can be undone by subtraction. Now the result of division, that's called the quotient. Looking at example 2.10, we can divide the product there, the result of the multiplication, 7560, by 24 to undo the multiplication. So we'll take the divisor and do the long division format here and put the dividend on the inside of that division symbol. And let's just start going here. We have 24. And we say, well, 24, that goes into 7 0 times, doesn't go into that, but it goes into 75 3 times, right? Because 24 times 3 is 72. And so then we could subtract 75 minus 72 is 3. Bring down a 6, and we can say, well, 24 goes into 36 one time, and so we subtract again 24 and 36. That result would be 12. Just move that example down a little bit. So 36 minus 24 is 12. Bring down the 0. 24 goes into 120 exactly 5 times. And so our remainder would be 0, so we just write 315 for the answer there. And so that did work. we got back to one of our original factors, and that helps us know that we did the multiplication correctly from example 2.10. Well, now let's do an example where we have a remainder. This one we didn't have a remainder. Let's do example 2.12. Find the quotient of 450 divided by 7. So 7 on the outside, we'll do long division format again. 450 on the inside. And 7 doesn't go into 4, but it goes into 45 6 times. So 7 times 6 is 42. Subtract, and 45 minus 42 is 3. Bring down the 0. 7 goes into 30 4 times. So we have 28 there. And subtract. 30 minus 28 is 2. And so we can say 64 capital R for remainder 2. We could also write that 64 and 2/7. And we could check our work on that too. We just do 64 times 7, add the remainder of 2 back to that. We should come up with 450. Now, one more way to divide this is to get a decimal result. So let's go ahead and do that. And what we need to do there is we'll just rewrite 7 into 450. And we can just work like we did before. 7 goes into 4 0 times. It goes into 45 6 times. So we'd have 42 there. Subtract, and we get 3. Bring down the 0. 7 goes into 30 4 times again, just like before. And that would be 28. And subtract and get 2. Now let's add a decimal place. Let's add that tenths place. And let's go ahead and do 4 zeros. That will do out to the 10,000s place. And we'll bring that first 0 down. And so that'd be 20. And 7 goes into 22 times. And that'd be 14 there. Subtract, and we get a 6 here. Bring down the next 0, so we'd have 60. 7 goes into 68 times. And so that would be a 56 here. Subtract, again, we'd have a 4. Bring down a 0. 7 goes into 45 times. And so that would be 35. And subtract, bring down, or we'd get a 5 from that. I'll just move that over here. We're kind of running out of room. We'd bring down that last 0 there to get 50. And 7 goes into 57 times. And so we'd have 7 times 7 is 49. 50 minus 49 is 1. We'd have to keep going with the decimals. We really aren't finished with that. But we'll just stop there, and we'll write that answer as 64. And the 2/7 part is 0.2857. And that's just the decimal form of 2/7 when we wrote it as a mixed number, 64 and 2/7. We'll cover decimal numbers and division with decimal quotients more in lesson 5, but for now just realize what we did there differently. We just added the place values on and added that decimal point right there, just using zeros as placeholders for the tenths, the hundredths, the thousandths, the 10,000ths place for this example. Let's do one more division problem. Look at this example. The farmer had $50 to spend on chickens. If the feed store sold chicks for $2.50 each, how many could the farmer purchase? Assume tax is included in the price. So basically what the farmers want to do is take his $50, break that up into how many chickens, divide it up. So we want to do a division problem here. So let's just go ahead and write it down. The $2.50, that's the divisor. So we put that here, 2.50, long division symbol, and 50 here. So we call this a story problem or a word problem, and basically what we have to do on a problem like this is figure out what are they asking us to do, and what tools do I need to solve that. Well, they're asking us to figure out how many chickens the farmer could purchase, and so how do I do that? Well, I need to divide these numbers. So now we have this division with these decimal numbers. What do we do about that? Well, we want to get rid of the decimals when we do division, kind of like when we did the multiplication earlier. So what we can do here is move the decimal to the right 2 in that divisor. And so we can do the same thing here. Move it to the right 2. We have to do it that way. Every time we move the decimal place, that's like multiplying by 10 when we move it to the right. So we've multiplied 2.5 by 100. We need to do the same with the 50. Multiply it by 100. And so we could even just rewrite this problem, 250 into 5,000. So now we can say, well, 250 goes into 500 2 times. So we have exactly 500 there. 500 minus 500 is 0. Bring down a 0. 250 goes into that 0 times, and we're done. 20. So for our answer, we can say 20 chicks. We could be descriptive about it, not just write 20, but 20 chicks. Okay, well that's all for lesson 2. Go ahead and do your problem set now and use your lecture notes to help you solve the problems as you need to. Use your rules and definitions. Turn the lecture back on too if that helps to solve the problems as well.